All right. Good morning. Good afternoon. Happy Monday. Sorry I'm not there today. I am proctoring an AP test. I'm not even sure which one. I can't remember right now. But I wanted to, because we're so short on time, I wanted to make sure we got through these first two sections so that we could test them up and get us through the year. Now, there's a couple things we're not going to do just to make um, the topic's not too crazy. But so today we're going to talk 9-1. I'll be back tomorrow and we will continue this. I can answer any questions you have, so nothing to stress about. I really just want you to get the notes down and give it a try. And you can check your answers and save questions, and I'll help you. So I guess here's the big idea. We are doing really the same thing that we did in Unit 8, but this one we are using categorical data. Right here, I'm talking about categorical things. Like if you look down here, never married, married, widowed, divorced, instead of having numbers that we could take an average of, or there was a percentage, that's what we did last unit. This unit, we're going to look at categorical data, and we're going to basically run a test to see if the data that we're getting with our sample is close enough to the population data in order for us to like agree with it. If it's too far away, then that would make us think that maybe the population data is wrong. Okay. So that's what we're going to do. We're going to run through the test. It's going to look real similar with a couple little differences. Okay, now the first thing we're going to have to do is we are going to have to, let me scroll down here. This is going to talk about segmented bar graphs. We will not be doing segmented bar graphs to save some time. So here's what we've got. We've got a census, the marital status right here. This percentage, this would be population percentages. So this is what the population is in the U.S. If we took a random sample, 500 adults, ages 25 to 29. So there's two things here. This would be called the observed. It's hard to write with this pen. This is the observed. Whoops, sorry, right here. These numbers right here, 260, 220, 0, 20. That's the observed data. That's when we sampled those 500 people. These are the answers we got. Now that's different than what we expected to get. The expected data is what the percentage will times the number of our sample. So for example, if I go down here, I had 500 people in the sample, 0.281, that's this number right here, changed to a decimal. And if you multiply those, I get 140.5. Yes, it doesn't make sense to have a half a person, but we're going to go with it. And in the end, it'll all work out. Okay, so we got 260. That's how many people said they were never married in the sample, but we would have expected to get 140.5. That's quite a bit off. Okay, married. This would take our 500 people in the sample. I would expect 56.3% of them. Change it to a decimal, multiply it out. Boom. There's this 281.5. Now, if I did widowed, I'd have 500 people in the sample times the percentage, 0.064. I did the math already, and it's 32. We would have expected 32. And then divorced would be 500 times 0.092, changing to a decimal. And 0.092 is 46. So that means we would have expected 46. So some of these are close, 220, 281. Some of these are way off, 260, 140, 032. So if they're close, then we'd be like, yeah, the sample looks a lot like the population. If they're far away, we will say like, no, this is something's funky, something's weird. Okay, and we'll run through a test to do that. All right, let me try and move this down. Create a segmented bar graph, not doing it. Not enough time. Not that big a deal either. Oh, I should back up the one thing I didn't mention. This whole thing, it's got a name. It's probably important we talk about that name. Boom, boom. It's called a, not chi, it's called a chi-squared test. And we're going to use this notation, big X squared. That's going to represent the chi-squared. And honestly, if you take stats again, they're going to make like this cool looking X like this. Chi-squared, they're going to call it. So let's talk about how we do a chi-squared test. Chi-squared test is got this weird, crazy looking formula right here. This funny looking E, that's Greek. You'll see fraternities, sororities, sigma, mostly fraternities. They use this symbol. This big E means sigma, which in the math world means sum. It means you're adding up all these different terms. And you're going to use this formula, observed minus expected squared divided by expected, and we add up all of them. Sometimes there's 2, sometimes there's 3, there could be 50. For the example that we did, we had 1, 2, 3, 4 categories. So we're going to do 4 calculations. So let me kind of scroll down. The chi-squared, this big X squared, this would be my observed, these numbers on top, these numbers on the bottom. Those are what we got when we multiplied on that other page. Those should look familiar. So if I go observed minus expected divided by expected squared, and I do that for the never married, boom, that's those numbers there. Here's my married numbers. Here's my widowed numbers. And here's my divorce numbers. You'll type all these out. You can do one at a time. You can do them all together. Just be careful. Make sure you have the parentheses around those numbers in the numerator on top. And if we crank all those out, we get a number. That number is weird looking X squared. That's our chi squared, hard to write, value. And we're going to use that on the table that you should have picked up when you walked in. Okay, so let's talk about how that table works. Okay, so the brand new, we're going to return back to this number, this 161 here in a second, but we're just going to practice with the table here. So here's how this is going to work. First off, there's this thing called a degrees of freedom. It's kind of a fancy name. And really all it is here, and this kind of chopped off, it's the number of categories minus 1. So for this problem back here, it would have been 1, 2, 3, 4 categories minus 1, which means the degrees of freedom would have been 3. Okay, so here's some just numbers thrown at you. Let's say we had a chi-squared of 8.36 and we had degrees of freedom of 4, which means there would have been 5 categories. All right, 8.36, I'm going to the table. This one is different. This one, I start here, degrees of freedom 4. 8.36, I'm moving along this table and I'm looking for where 8.36 would have been. It would have been in between these two numbers. Okay. Now, we can't lock in what our p-value is, but we can get a good idea. This tells me that the p-value is in between those two numbers. So if I go back here, p-value, whoops, is between 0.5 and 0.1. We're not going to get perfect, but we're going to get good enough where we can say either reject or do not reject. Okay, for example, like if we were comparing to 0.5, I would know that no matter, I don't know what it is, but I know it's going to be bigger than 0.5. Okay, let's try this one. 10.27 degrees of freedom of 10. So I'm going back here. I'm going to clear this off. degrees of freedom of 10, which means I'm on this row, 10.27. 10.27, it is not on here at all. It's actually going to be on this side. It's going to be somewhere over here. That number is going to be somewhere here. Okay. So and they go off the table. Sometimes they'll be off the table over here on the right. Sometimes they're on the left. If I'm on the left, then that means my p-value is going to be bigger than 0.25. I'm going to go back here. I'm going to say greater than 0.25. Okay, let's try this one. 25.23, 6 degrees of freedom. I'm going to go back here. I'm going to clear this off. I'm going to go to the 6 degrees of freedom. 25, boop, 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 like I'm going along. It's going to be way over here. If you're way over to the right, then that means my p-value is going to be teeny tiny. It's going to be less than 0.001. Less, whoa, my gosh, I keep shrinking that up. Less than 0.001. Okay, so that's how we use that table. All right, so how do we do a test? This is going to be, these are quicker than the other one. So this kind of walks you through what the test looks like. Okay, so I am going to just slide down here and we're going to kind of walk through it. Okay, the first thing, the parameters, all we do is this. It's easy. There's one thing. Sometimes it'll be a different significance level, but usually it's that 0.05. Okay, hypothesis. Okay, the hypothesis is always the same value or the same thing. Okay, this would be there is no difference between observed and expected data. Every time. That's what you're going to put. The alternative hypothesis is, guess what? There is a difference between observed and expected. Sorry, this is sloppy. Okay, so that is the H. Boom, hypotheses done. Okay, C, the conditions. I'm just going to slide up here. It's got to be random. These are all going to be random samples. All our expected values need to be bigger than 1. And 80% of the expected values are bigger than 5. Okay? Not all of them, just 80% of them. And if I go back to this example that we had from before, all of our expected values were bigger than 5. So we're good there. So if I slide back here, check, this was my H. Check conditions, check. All of those checked. Segmented bar graph, not doing that. T, find the chi-squared. Okay, chi-squared. We already figured it out. It was 161 points. I'm looking at my notes so I don't have to flip back. 0.77. Degrees of freedom. We had 4 categories. -1 equals 3. Okay, so now I want to find the p-value. I'm going to go to my chart. I'm going to go to degrees of freedom 3. I'm looking for a 161. Holy cow, it's way over here, which means my p-value is less than 0.001. Less than 0.001. That's a weird less than. There we go. Okay. So now A, we compare to alpha. If it's less than 0.001, I'm just going to say, let's just say it is 0.001. It's even smaller than that. And if I compare it to the alpha, it's way less, which means we reject the null hypothesis. That means we're rejecting the null, which means we're going with the alternative, which means there is a difference between the observed and expected. They were far enough apart for us to say, oh, those aren't close. Those aren't close. They're too far away, too far apart. Okay, and that would be our conclusion, rejecting the null hypothesis. If the p-value was greater, we would do not reject the null, which means we would say there is no difference because they're close enough to say, oh, no difference. Okay, so give it a go. Give these a try. I think there's a couple of problems you can try on the worksheet today. Check answers, save questions, and we'll talk about it tomorrow. Okay, thanks. Oops.